जी अस्सलाम वालेकुम स्टूडेंट्स। आई होप यू विल बी फाइन। और मेरी आवाज़ आ रही होगी आपको। सो आज की इस डिस्कशन में आई विल बी डूइंग फिजिक्स पेपर 2 न्यूक्लियर फिजिक्स पास्ट पेपर क्वेश्चंस। सो इफ़ you have any problem in physics paper 2 questions related to nuclear physics, then this video is for you. I will be solving 3 questions from latest past papers so that you have a better idea of what type of questions will you face in nuclear physics. So let's get started. So this is our first question that is taken from sorry. The first question is from October number 2024 paper 2-2. So you can read the statement of the first question. Compare an alpha particle and beta positive particle in terms of their masses and their charges. So you know alpha particle is represented by it's like a helium nuclei, and it has two protons and two neutrons. So nucleons are 4 and protons are 2. So that means the charge on this particle would be positive 2e. Okay, as there are two protons and elementary charge is e, so the charge would be 2e, charge on alpha particle. Okay. And what is charge on beta positive? If you compare beta positive, that it has charge of 1e and its nucleon number is 0. So charge would be positive e. So if you will write over here, then you will say that the charge of alpha particle is 2e and the charge of beta positive is e. Both have positive charges, and the magnitude of charge of alpha is twice the charge of beta positive. What about their masses? You know, in alpha there are 4 nucleons. Okay, there are 2 protons and 2 neutrons. And in beta positive, the mass of beta positive is equal to the mass of electron. And you know that mass of proton is much greater than the mass of electron. So you will say the mass of alpha particle is much greater than the beta positive particles. So the first thing is the mass of beta positive is mass of alpha particle is much greater than the mass of beta positive particle. And the second thing, both have positive charge. And the third thing, the magnitude of charge on alpha is twice the magnitude of charge on beta. So these are 3 points you have to mention over here. Nucleus P, that is drawn over here, it has nucleon number 216 and proton number 84, undergoes alpha decay to form nucleus Q. Q is not shown over here. Nucleus Q then undergoes a further decay to form nucleus R. The proton and nucleon numbers of P and R are shown. Okay. On figure, draw a cross to show a proton number and nucleon number of nucleus Q. Okay, so when P decays alpha particle, then nucleus Q is formed. So first of all, we should write the equation for this decay. You know, P is proton numbers of P are 84 and nucleon number are 216. When alpha particle is emitted, Q is formed, and you know alpha is 2, 4. In any reaction, the charge number is conserved. If the charge number, proton number on the left hand side is 84, then the total proton numbers on the right hand side must be 84. So that means you can easily write what should be the proton number of this Q. There must be 82. 82 plus 2 makes 84. And nucleon number is also conserved. So 216 minus 4 would be equal to 212. So now we can easily identify Q on this grid diagram. It must have 82 as proton number and nucleon number should be 212. So you can see from this diagram 82 and 212 comes here. So here you will mark with letter X as Q. Okay. So in figure, draw a cross to show the proton number and nucleon number of Q. Label your cross at Q. So we have labeled it as Q, and Q has these specifications. State the names of particles emitted as Q decays to form R. You know, if Q decays, it forms an R, and if you can see from this diagram, proton number is increased by 1. Proton number of R is 83 and proton number of Q is 82. So proton number is increased by 1 and nucleon number is unchanged. If you know the basic equation of beta positive and beta negative particles, so write Q is 82 and 212 and R has 83 and 212. You know that beta, if I say beta negative is emitted, then beta negative has proton number of -1. So -1 plus 83 will make 82 and this number is 0. So beta negative is emitted from Q to form R. Why not beta positive? You know, when beta negative emitted, it increases the proton number by 1 and keeps the nucleon number same because the nucleon number of beta negative is 0 and proton number of beta negative is -1. So if, for example, instead of R, the proton number of this R is, for example, 81, then beta positive would have been emitted. But in our case, we know that proton number of R is 1 more than the proton number of Q, so beta negative is emitted. You will simply write beta negative. Okay. Particles emitted are beta minus, you can say, and you know that state the names of particles emitted. When beta negative is emitted, beta minus is emitted. In addition to beta negative, another particle is emitted, which is known as electron antineutrino. Electron antineutrino has no charge. Okay. So when beta negative is emitted, you should keep in mind that electron antineutrino is emitted. So over here you will mention beta minus, beta negative, and electron antineutrino. Electron anti-neutrino. In any reaction, lepton number must also conserve. How would you keep this in mind? As you know that this is a lepton and the lepton number of a particle is 1 and lepton number of this is also lepton and this is anti particle. So lepton number of anti particle is -1. These are particles. These are not the lepton number at the reactant side is 0 and lepton number on the product side should also be add up to 0. This is an interesting part. Before the alpha decay, P is traveling at constant velocity in this direction. After the decay, Q has velocity of 1.3 times 10 power 5 ms minus 1 and alpha at an angle of 68 to the original path. Alpha particle has velocity this and the angle is theta. So what you have to find, use the principle of conservation of momentum to determine theta. Okay. So here we have to use conservation of momentum. So this is two-dimensional Coulomb case. So the momentum in both directions, in x direction and y direction, will conserve. So how to write the equations for initially we don't know the speed of this particle, okay, but its momentum is along x-axis. There is no vertical component of momentum. So if the vertical momentum before is 0, then the total vertical momentum after must be 0. So here I should write the equation for vertical momentum. I am using the conservation of momentum and momentum of P along y direction is 0 before and momentum of this particle has vertical component which is, you can easily see, the mass of alpha. How would you find the mass of alpha particle? You know that alpha has 2 proton and the nucleon number is 4. So the mass of alpha is 4 times unified atomic mass unit. The value of U can be obtained from the first page of your paper. So the mass of any nucleus, any nuclei is equal to the nucleon number times unified atomic mass unit, whose value I will mention later. So the velocity of this particle is this one. So this component, vertical component will be 4u, this is m, time velocity, which is 150 times 10 power 5 times sine of theta. Because this is vertical component, so this should be written with sine theta. So I will mention over here 4u times 150 10 power 5 sine of theta, and the vertical component of Q would be in downward direction and the velocity of Q is this. What is the nucleon number of Q? You can see from here. The nucleon number of Q is 212. So the mass of Q would be 212 U time. So 212 U, this is mass, time its velocity, 1.3 times 10 power 5 time sine of 68. So I will equate these two vertical components of momentum as the total vertical momentum before is 0. So I can write over here plus, as this is in downward direction, so it must be written with negative sign. So I will write 212 U time 1.3 time 10 power 5 times sine of theta. So U will cancel out. So there is no need to worry about its value if you don't know. But on your front page of the paper, the value of U is mentioned over there and you can use that value if you want. That is the value of u is 1.66 times 10 power minus 27 kg. Okay, so just mention a negative sign over here and solve for theta from this equation. You can easily solve, so there is no problem how to solve this equation. Okay. So I will be bringing this term on the other side, which is 212 into 1.3 into 10 power 5 into sine of, I should put the value of theta over here, which is 68. I'm sorry, 1.3 10 power 5 sine of 68 is equal to 4 times 150 times 10 power 5 sine of theta. So you know how to solve it, this equation for theta. You will bring these numbers from this right side to the denominator of the left side, and then after simplification you will take sine inverse of this equation. Your answer for theta should be 25 degree. So theta should be 25 degree. Simplify it. I will not waste your time in finding the value of theta, which you already know. Calculate the kinetic energy of alpha particle. So now, how can you find the kinetic energy of alpha particle? You know, the speed of alpha particle is given, which is 150 times 10 power 5, and the mass of alpha particle is 4u. So the kinetic energy would be, you already know that kinetic energy is half mv square, and the mass of alpha particle is 4u time its speed, which is mentioned clearly in the question, 150 times 10 power 5. You have to take square of this whole number. Mostly students forget to take the square of this quantity. So now you have to put the value of u, which is, first you should simplify this, 2 times value of u is 1.66 times 10 power minus 27 times square of this whole quantity. Use your calculator to evaluate this quantity, and your final answer should be 7.5 times 10 power minus 13 joule. I hope you know the rules of rounding. If the question is given in two significant figures, as you know, all data is given into two significant figures, 1.3 times 10 power 5 and two significant figures. This last zeros can be significant or it can't be. It depends on the rounding. So if you have multiple significant figures involved in any question, and there is division and multiplication involved, then you have to take least significant figures. That's why your answer for this part is rounded to two significant figures. Okay. So this was a question related to the conservation of momentum, and it was involving nuclear particles. Okay. What if you have to find the velocity of this P? That is not mentioned in the question, but what if you were supposed to find the velocity with which this was moving? I hope you can find. You should use the horizontal component of momentum, conservation of momentum along x-axis, and the momentum of P would be, we have to find its velocity. So I will mention over here, you know what I want to find? I want to find velocity of P before impact. So mass of P, I will be using conservation of momentum along x-axis, and the mass of P would be 216 time atomic mass unit, 216 times U. This is mass time its velocity. This is momentum along x-axis. I should revise the concept. The conservation of momentum in any direction should be, the momentum in any direction should be conserved. So momentum along x-axis should also conserved, and now we are using the x component of momentum. And momentum of alpha particle along x-axis would be 4u, this is mass, time its velocity, which is 150 times 10 power 5. This is momentum, and its component would be cos of theta. And momentum of the lower particle q along x-axis would be mass of q time velocity of q time cos of 68. So 4u time 150 time 10 power 5 cos of theta, we have obtained cos of 25 plus mass of q is 212u time 1.3 time 10 power 5 times sine of 68. This equation will give you the value of V. That was not mentioned in the paper, but you should find it. You should think beyond the paper. Now let's do the second question. I will recommend you to read this question and try to fill this paper table. I will give you 2 minutes so that you can do it by yourself. I always recommend student must try it. Okay, I hope you have done the completion of this paper. This question is based on your fact. You have to mention the charge of up quark and charge of anti up quark, charge of down quark, and charge of anti down quark, and charge of strange quark. Meanwhile, I am unable to see your comments. Let me see who is commenting. Okay, that's good. So what is charge of up quark? Charge of up quark is, this is positive 2 by 3 time E. E is elementary charge. And the examiner have mentioned E in the table. It has made this as unit. So you should write 2 by 3, just 2 by 3. And charge of anti-quark of any quark is negative of that charge, which is negative 2 by 3. And charge of down quark is, what is charge of down quark? Down quark is negative 1 by 3, and down anti-quark would be positive 1 by 3. and charge of strange is negative 1 by 3, and charge of strange antiquark would be positive 1 by 3. So very simple, very simple. Sorry, I should not mention E over here because this is mentioned in the heading. You know how what is the quark composition of proton? You know, proton, the charge on proton is positive 1 e, and it is made up of three quarks, two up and one down. And you know that up is 2 by 3 e, plus another up is 2 by 3 e, and the down is minus 1 by 3 e. If you add all these three, you will get 3e by 3, which is e. Okay, so you should know the quark composition of proton and neutron. State the name of class of fundamental particles to which baryons and mesons, class group of fundamental particles to which baryons and mesons belong. Okay, so you know that this is also a very simple question. Baryons are based on three quarks. Baryons are composed of three quarks, and mesons are composed of one quark and one antiquark. So baryons, three quarks, you will write in a sentence, and mesons are composed of one quark and one antiquark. One quark and one antiquark. And if you have to mention the example of baryon, you should write proton, because proton is composed of three quarks. Neutron is also a baryon. Compare baryons and mesons in terms of, here in this part, state the name of class of fundamental particles to which baryons and mesons belong. So baryons and mesons, this is the question, the solution I have written, this is the answer of the second part. He is mentioning over here. So we have to write the baryons and meson in terms of their particles. Here we have to just mention their class or group. You know that there are two major classes of all particles: hadrons and leptons. Leptons are fundamental particles, whereas hadrons are not fundamental particles. Hadrons are composed of quarks. So baryons and mesons, they are hadrons. Definitely, they are hadrons. They are not leptons, as they are formed by quarks and antiquarks. So baryons, three quarks, and meson, one quark and one antiquark. Describe beta positive decay in terms of fundamental particles involved. You know, if I write the equation of beta particles, beta positive particles, for example, if you have a neutron and the charge on neutron is 0 and nucleon number is 1, if, for example, this changes to proton, which is 1 and 1, what should be emitted? Beta negative should be emitted in this case, because positive 1, negative 1 will add up to 0. So this 1 and that 0 are equal to 1. So when a neutron changes to proton, then beta negative is emitted. This is beta negative. And apart from this, with beta negative, an antineutrino will also be emitted. Okay. So when proton changes to neutron, which is 0, 1, what should be emitted? You should tell me. This is positive 1 and that must be 0. So that nucleon number and proton numbers are conserved. So this is beta positive emission. And with that, a neutrino will be emitted. Okay. So you have to memorize this equation. So we have to mention beta positive decay in terms of fundamental particles. So proton is not fundamental particles, neutron is not fundamental particles. So we have to mention in terms of fundamental particles. So proton is based on three quarks, up, up, down, whereas neutron is up, down, down. So you can see which quark is converted to which quark. If you compare two up, one down to one up, two down, so up is converted to down. So up quark changes to down and beta positive is emitted. So you have to mention, you have to write this equation in terms of fundamental particles involved. So what are the fundamental particles? One is up quark and other is down quark. You will say up quark changes to down quark and positron and electron antineutrino are emitted. This is positron, this is electron neutrino, this is electron neutrino, this is positron. So these all are fundamental particles. So you have to describe this beta decay in terms of fundamental particles involved. Okay. So if you were asked to describe this beta negative decay, then you should mention this, that neutron changes to proton. In other words, up, down, down. In other words, down quark changes to up quark, and antineutrino will be emitted. So I have mentioned both equations. So it depends on the examiner. What does it he prefers? So question number, this is the third question that we have to answer. Nuclei of an isotope of copper each have 29 protons and 37 neutrons. This isotope is a beta emitter. State the nuclide notation in the form of X, A, Z for this nucleus of copper. Very simple. Z shows number of protons, and in this you have the symbol of this is mentioned, Cu, and total protons are 29. So you will write 29 over here. And the upper number is nucleon number, and nucleon number is proton plus neutrons, and there are 29 protons and 37 neutrons, and if we add them we will get 66. So 66 nucleons are there in this isotope of copper. So you have to write this basic notation of this. The energy spectrum of beta negative radiation emitted by a sample of this isotope is shown in this. It's a number of beta particles, and over here you have a kinetic energy. And if you look at this graph, there is a range of kinetic energy. Okay, the range of kinetic energy means the kinetic energy lies from this value to that value. So there is any kinetic energy between these two values are possible. So there is a continuous range of kinetic energy of these beta particles. Let's see what does examiner expect. Use this figure to explain why other particles apart from beta particles must be emitted during this decay. Okay, so we have to explain why there must be any other particle. This graph was the reason of the discovery of neutrino and antineutrino. As you know, alpha particles have specific kinetic energy. If you have alpha particles, they will have a specific kinetic energy like this. All particles will have this specific kinetic energy. But in this case, there is a range of kinetic energy. Different particles have different amount of kinetic energy. So we have to explain why this have this type of shape. Why other particles must be emitted. So you know that the energy of any decay is fixed. In any decay, what quantities are conserved? You know, any decay, energy mass is conserved. In other words, in any decay, mass can be converted to energy. So if the mass of product is smaller than the mass of reactants, then the difference of mass is converted to energy by the famous Einstein equation E equal to mc square. This equation shows mass energy equivalence. So in any reaction, the difference of mass is fixed. So we can say that energy of decay is constant. Energy of any decay is constant. So if energy of decay is constant and beta have range of energies, that means some other particles must be emitted. They share the difference of energy. So energy of beta particles have continuous range of values as energy of that graph shows beta particles have range of kinetic energy. So another particle that you should know in this case, which is antineutrino, must be emitted. If I write the equation of this decay, this copper is basically beta emitter, and for example, X is formed and beta negative is -1 and 0. So this must be 30 and that is 66. So apart from this beta negative, a neutrino with beta negative, as you know that beta is a particle, so antineutrino must be emitted. So these two particles share energy between themselves. So this is the mass of these products is smaller, will be smaller than the mass of this reactant. So the mass is converted to energy. And if there is no other particle, like if we suppose there is no beta negative, there is no antineutrino, then the energy of kinetic energy of this will be constant, like alpha particle. But in this case, if the kinetic energy has range of values, then another particle must be emitted. If this is beta positive, then neutrino will be emitted. State the name of other particles emitted during this reaction. I have mentioned one particle would be beta Electron, this is electron antineutrino. So you have to mention over here the electron antineutrino. The copper isotope decays to an isotope of zinc. I just mentioned the name of zinc with X. I didn't know that. What will be emitted? So give the radioactive decay equation for this decay. Include the nucleon and proton numbers of all the particles involved. I have already done. Over here, you have to mention zinc. Zn. This is zinc. So this is the equation, and you have to mention these particles. This is a 3-mark question. 1 mark, the values of for proton number and nucleon number, and second for beta negative, which is -1. Over here, you will write its proper symbol, which is beta -1 and 0. And then you will mention antineutrino with 0 charge and 0 nucleon number. As the examiner requires to give the radioactive decay equation include the nucleon and proton numbers of all the particles. If you will not write the proton number and nucleon number of any particle, you will not get full marks. So that was the session, and I hope your basic idea would be clear that how to answer nuclear physics questions. Okay, see you in next video. I am now signing